Quick summary of today's class. We have displacements along 3 ramps, and we assume that the ball can go from one ramp to the next without any loss of kinetic energy, except that associated with the loss of potential energy. Now, we have the 3 displacements, delta x1, delta x2, delta x3, and we draw those 3 displacements here, here, and here, along with the weight vector, and we look at the projections of the displacement vectors on the weight vectors. And those projections give us the changes in the y-coordinate, in the altitude of the ball. Now, these pictures aren't done, and we didn't even try to do them so that they completely match this picture, but if done correctly, the delta y1 here and the delta y2 here are both down. The delta y3 here would have to be equal to the sum of the delta y1 and the delta y2. Looks like it's a little bigger than either of these, but it's certainly not equal to the sum, because I simply didn't make the delta x3 steep enough and probably not long enough either. But if the diagrams are drawn correctly, we'll see that the delta y's add up to 0. Now, I can then say that clearly the delta y1 plus delta y2 plus delta y3 would be 0, as again would be shown by an accurate set of diagrams, or if you have the calculation, if you have the actual vectors, calculate the projections, and you would find that the delta y's do add up to 0. Okay, we conclude from this then that the work done by gravity, the total work done by gravity from here to here to here to here, in other words from here around and back, is equal to 0. Now I assert this, and I asked the class to prove it, and got some pretty good responses, but the thing that this really comes down to is simply that since the weight is constant, the weight vector is the same in every case, then if we're multiplying the weight vector by a y1, then a y2, then a y3, when the delta y1, delta y2, and delta y3 add up to 0, the product has to add up to 0. Okay, so since the weight is constant, we can write that formally. Delta grav total is the weight times delta y dotted with delta y1 plus a weight dotted with delta y2 plus a weight dotted with delta y3. Those dot products, which involve in each case multiplying this projection by this vector, clearly then have to add up to 0. They add up to the weight dotted with the delta y1 plus delta y2 plus delta y3, using the fact that the dot product is associative. It is distributive. The dot product distributes over sums. And we conclude that the weight dot 0 equals the weight dotted. We conclude that this sum, since the delta y1 through delta y3 add up to the 0 vector, is just the weight dotted with the 0 vector, which is 0, meaning that gravity does 0 work on this ball as it travels this closed path. If I draw another closed path with a bunch of short vectors, okay, even if the path crosses itself, it doesn't matter as long as it comes back to its original point, then the work around that path also has to be 0, because you could do exactly the same thing with these vectors. You would have more of them, but everything would be the same. All the delta y's add up to 0 if you come back to the same point, and that should be fairly obvious. So this can be extended to any sequence of vectors, but any sequence of vectors, well, we could, if we have a closed loop, if we start at one point, move around the loop to another point, back to the same point, we could break this into very short intervals and have a lot of little vectors here. And the little vectors would always, no matter how short the intervals we use, would always have y projections that add up to 0, because the weight vector is always the same. We're doing exactly the same thing. And if we take the limit as the greatest length of any of these vectors approaches 0, we get what's actually a line integral. But you don't have to know that. But we do get the sum over the curve, and we're going to get the same result. The product, or the sum of all the work contributions all around the curve is going to be 0.